So welcome from my side, and also welcome. Thank you very much for inviting us. Actually, so I got the first request to give a talk on this topic, and then I said, well, we have a group member who's working like mainly on this topic. So I thought that Svenja could present this topic, but unfortunately, I have to give the talk on behalf of her because she couldn't attend on short notice. So the credits on the slides and the preparations go on her, but it's a topic that we considered together where we collaborated. So I'm happy to present this joint work today. So the title of this talk is Security of Code-Based PIR, where PIR stands for Private Information Retrieval Schemes. And whenever you start papers or talks on the security it's just a nice way of saying that something isn't secure, right? So usually there is a result behind that stating that it isn't actually secure. And it's also going to be the same in this talk. Okay, so here's the outline of the talk. So first, I'll give a very short introduction, very high-level introduction to private information retrieval. And after that, we'll have a look at some existing approaches and also discuss the limitations. And then we'll give a quick summary on the lessons learned from this analysis that we did so far. Okay, so what is the setup? So basically we have let me check it if it works. So we have a client here, and this client wants to obtain a file with index I0 from a database, which is basically the server here. So it's stored on the server here. And so in order to obtain this file, it sends a query to the server and hopefully gets an answer from which the client can then extract the desired file. But now it's private information retrieval, namely we want to hide the index of the file from the server. So the server should not learn anything about the file that I'm actually requesting. And so you could think about several scenarios. So for example, if you have like a search database, so the server doesn't want to learn about what you're searching, or if you have like a storage system, you don't want the server to learn something about the index of the file. So there are several scenarios that can be considered there. Well, there is two methods to do this. So if you're considering information theoretic security, there is a very trivial approach, and unfortunately it's for the single server case, it's the only one that's provable secure. It's namely download the entire database, right? Whenever I download the entire database, the server doesn't learn anything about my file. But whenever you access a database, you don't want to download it every time, right? So that's not efficient. For multiple servers, there is an efficient solution, but only under the assumption of non-colluding servers. Yeah. But when we move to practice and away from the information theoretic security, we can discuss the so-called computational security. So that's something we know, for example, from asymmetric cryptography, from public key cryptography. So basically, we can base our security on a computationally hard problem. Yeah, and that's actually, there is some approaches to do this. So this is possible in the single server scenario, which is actually also the one where we don't have an efficient information theoretic solution. And we can also think about already the latest developments, is namely to think about in the context of asymmetric cryptography, about quantum resistant or post-quantum cryptographic schemes. And most of them currently, they're based on hard problems from lattice theory. So there are lattice-based schemes, but there also exist other schemes like code-based schemes. So some of you might know the Macaulay crypto system as one of the prominent examples. And there are many variants based on different underlying problems, but most of them are currently lattice-based. And however, there is alternative assumptions such as code-based, as I mentioned, and this is important also to have something available in case there is, for example, new developments in the cryptanalysis of lattice-based schemes. It's important to have more diverse directions, yeah, because otherwise maybe it's an issue for all the available lattice-based schemes. So that's also, for example, for the PQC schemes, for the public key schemes, there is a standardization going on at NIST, and for the signatures, for example, there were only signature schemes based on certain assumptions. They even made a new call. One of the big reasons behind that was actually that there was not enough diversity of the underlying technologies. Yeah. So you really want to spread. That's why code-based approaches are in general desirable. And it's also one of the older hard problems actually that I used. So McAleese in its original form, it's still secure even after many years of cryptanalysis. Okay, so just to get some notation together, so we consider a linear code C, so in length n, dimension k. So that's a k-dimensional subspace of this vector space over FQ there, where FQ is a finite field of order Q. And the nice thing about linear codes is we can represent it by a generator matrix. So basically the rows of G are simply a basis for the considered subspace. And encoding can also be done simply by taking the product of a vector M with this generator matrix G. And one notion that we need when talking about this code-based PIR schemes is that any set of k-linear independent columns of G is called an information set. So basically, that's exactly the number of columns of the generator matrix that you need to recover basically your information in the error-free case. So in code-based cryptography, actually, so the basic setting is the following. So we have a message M, and in order to encrypt this message, we simply map it onto a code word of our linear code C. So we perform the encoding here and map it to a code word, and we may add an artificial error E to this. So this is very different from communication. So usually it's something where you cannot control the error in a sense. So it's given by a channel or by some physical effects that occur. But in crypto, it's something you can design, which is very nice on one hand, but we also see the limitations in the end. So basically we add an artificial error, and we say that in our case, we consider the Hamming metric. We say that the Hamming weight of this error is within the error correction capability of our code. And we have additional assumption that G has a secret hidden structure, which allows the entitled user to decode efficiently. Yeah? So that's something, we need an efficient decoder for our code. On the other hand, my generator matrix, which is sort of the public key that I provide, it should look random to anyone else. And that's a very challenging thing. So basically, it should have structure on one hand, because we need an efficient decoder. On the other hand, it should look random to someone else. So we should hide the structure from the attacker. And that's the big challenge. Yeah? And whenever there's new papers saying that a new scheme is broken within several hours or over the weekend, usually it's a structure that you can exploit in the end. What is the hardness assumption behind this in general? So the assumption is that decoding a noisy code word from a random linear code is in general hard. Random linear in this case means so it doesn't have a particular structure that we can exploit in order to decode efficiently. And as already mentioned, one of the most prominent examples is the McAleese crypto system, which is basically as old as public key cryptography. So in the end of the 70s, and it's based on Gopper codes, and it was a very fortunate choice in the terms of security. As I said, it has never been broken. However, the public keys are super large. Yeah? In order to reduce the key size, one could introduce structure, but this again is very dangerous because it could also be exploited by an attacker. Now, let's have a look at the generic PIR approach. So again, we have a client here on this side, and it wishes to get the file within file X with index I0. and we have the database, which basically has all the files stored there. And the client then generates a query. So we assume, or here we denote by N linear homomorphic encryption scheme. So homomorphic means I can perform operations on the ciphertext without decrypting. Yeah, so I can, for example, if I want to add ciphertext or multiply them, I don't need to decrypt them. I can operate on the encrypted, on the ciphertext themselves. And then for each of the files, we calculate some QI with this property, so which is the encryption of 0 if our index is not our desired file index, or encryption of 1 if our index is exactly the file that we want to download. And then we send this query to the server, and this generates then an answer, and it's basically just the sum of the product of the xi and the qi, which in the end is then basically the encryption of my file that I desired. And so at the client, I can simply recover the file by decrypting it. Okay, so let's have a look at what the requirements are on the code-based side. So we need secret or public key encryption, as already spoiled. So there is code-based schemes available. So this is very easy to check that it works. And we need the encryption of n particular plain text under the same key. So also this is something we can ensure. And we can perform scalar multiplication on ciphertext. So ciphertext in our case here are simply code word plus error. So we are considering this sort of Macaulay setting. And if I do just a scalar multiplication, so if I take this code word plus error, multiply it with a scalar, the Hamming weight of the resulting ciphertext does not change. Yeah? So we do not increase the Hamming weight, meaning that I still can decode, or the legitimate user can still decode. And basically, due to the linearity of the code, I have the desired property. Now, what about the addition? Well, when talking about homomorphic encryption, usually you get one operation almost for free. And as you can see, in this case, it's basically the scalar multiplication. When it comes to addition, this is not necessarily working, right? Because if like the support of these vectors, of the error vectors, is not the same, then I will increase my Hamming weight. Yeah. So meaning that maybe I can do it. Maybe the code is good enough such that I can like perform 2 or 3 additions, but then I have to recover it, which is called bootstrapping, and that's usually a very demanding step. Yeah? And this is very limiting in terms of performance. So that's why homomorphic schemes, also lattice-based schemes, are still very, very computationally inefficient. So this is something we have to worry about. And so if the other question is, if we can kind of come up with a code-based scheme, is it more efficient than the trivial solution? Because in the end, it should also be better than what's out there, right? Okay, so let's have a closer look. So let's see what existing approaches are out there. We've seen that the addition of several ciphertexts can be an issue because it can increase the error weight. However, what you can do is you can restrict the support of your error, saying that if you take 2 ciphertexts and you add them, you just require that they have the same support. Because then I hit basically the same erroneous positions when I perform the sum, and then I can add up as many ciphertexts as possible. So one could say, well, that's easy. So the disadvantages are that, of course, if I restrict my error support, this adds additional structure, right? So this could weaken the security of my schemes. And this can be also exploited by an attacker in the end. Okay, without this structure, so what is the underlying security model? So the underlying security, or what is the hard problem? It's the so-called information set decoding problem. So whenever I have a generator matrix of a code, then a matrix R and some integer T, then I will, exactly. Then I decide whether there exists an error matrix of this dimension of weight at most t, such that every row of this R minus E is in G, which means that it's a code word. So it's a bit different than the classical information set decoding problem, because here I'm considering matrices instead of just a single code word. Yeah, so it's a sort of interleaf decoding problem. And what are the best known attacks? So there is algorithms for information set decoding. There's also some progress going on there with several variants. One could also reduce this to finding low weight code words, because you could simply stack the generator matrix and basically your ciphertext, which is a code word plus an error, and then find in this space a vector of low weight. And if I consider this interleaf decoding problem, there is a very efficient algorithm by Metzler and Kapturowski, which works for very high order interleaving. So what does interleaving mean? Interleaving means I stack basically several code words, and I consider an error model where basically all the error vectors share the same support. Yeah, so I basically extend the Hamming weight to matrices. So I consider columns that are erroneous. And this decoder can decode up to d-2 with high probability, exactly, whenever my interleaving order, which is the number of code words that I stack, is larger than the error weight I want to correct. And this works for any code, for any random linear code. You don't even need an efficient decoder for the component code, and it has only a cubic complexity in a very naive implementation. So it's a very powerful tool. And when it comes to crypto and you stack lots of code words, so immediately Metzner-Kapturowski comes to your mind, because it's very efficient and it works for these cases. Okay, what's even worse there? We have additional structure. Why is that? When I want to now use a code-based scheme and use it as a PIR scheme, I somehow have to hide my index in there in a way that I can then recover it again at the client. And there is two chances to do this. So I can do this in the plain text part, so basically in my message, or I can do it in the error. And in order to do so, you need to introduce additional algebraic structure. And this allows for structural attacks. So ISD may not be the most efficient attack anymore, which in turn lowers the security level. So let's have a look. Here we have a concrete example. So it's a scheme, one of the first code-based schemes that was introduced by Holzbauer, Lanti, and Wachter C. And oh, we're running out of battery. Okay. So here we take an extension field of FQ of degree S, and I consider it basically as a basis gamma 1 to gamma S. So it's a basis of FQS over FQ. And I divide this basis into two subspaces. So the first one is V, it's gamma 1 up to gamma V. And W, which is gamma V plus 1 up to gamma S. And then I form a query of this form, which I discuss in a second. So when talking about security, we just look at the query at the moment, because that's the crucial part, because that's what's sent to the server. Yeah. So and of course we need to make sure that the server cannot learn from our query about the file index. So what is this? So this is a matrix Q, which has dimension m times delta times n, where basically D is a matrix where all the rows are code words of a random linear code. Yeah, I don't care what code it is at the moment, but it's a random linear code. And so I mentioned it, interleaving, basically that's an interleave code word, right? And the interleaving order is rather large. Then I have a part which is this error matrix E here, and you see the error support here is restricted. So all the component errors, if I look at the rows, they all share the same support. And additionally, these entries of E are taken from this subspace V that we defined here, okay? And then we have another component. We have a matrix delta, which has a full rank, by the way, and its entries are chosen from the subspace W. And it's a small matrix, and by taking this Kronecker product here, I basically shift this matrix to a certain part. Yeah. And as you can see, so EI naught is basically the identity, the unit vector with index I naught, so the file index that I want to have. So basically I encode the information about my file that I want to get by shifting this matrix delta to this particular position. Okay, so far so good. So I don't care about recovering the file now. So basically, by taking the product of the database with this matrix Q, sending back the answer, the client can recover the desired file. Okay, now the original security claims relied on interleave decoding attacks, so they considered it, and also a so-called subspace attacks. So by looking at the two subspaces where the error values are chosen from. However, there was a subquery attack proposed that recovers the file index, unfortunately, so which breaks the schemes. And what is based on is the following observation. So let me jump back. So what we know is that basically this first part here, so this D plus E, so this matrix has rather low rank. Yeah. So if I considered only this part, this has rather low rank. Yeah. However, the rank is increased since I add this delta dependent part where my index is encoded. So this increases the overall rank. And basically what the subquery attack does is it takes out from this big matrix one by one always blocks of size delta here. And whenever you remove the block where basically the delta dependent part, so my file index is there, the rank of the entire matrix will drop immediately. Yeah? And this is how you can recover the file index I naught. Yeah? So that's basically the idea behind this subquery attack. So you divide the query matrix into m blocks of the desired index, and then you can find it by just checking the rank. Yeah. That's just exactly. So that's basically a matrix where the rows consist of code words of a random code. Yeah. So basically, the error matrix E is basically there. You can consider this as sort of a make-a-least type system. Yeah. So you have code word plus error from a random code, and it's very hard to decode. But that would be the classical setup. So basically here, what you have here is you have an additional matrix where you hide the index. It's not only about public key crypto, it's additionally encoding the index. And that's done by this additional error back here. And it has the same error support, so that's also worth mentioning. It has the same error support as the matrix E. Yeah, so basically you do not increase the Hamming weight of the matrix if you consider it column-wise. Yeah. Okay. Okay, so that was basically an approach to break the scheme, and now they repaired the scheme. Yeah, so they proposed a repair of the scheme, and the main idea was, since it was very bad that basically the index part was only hidden in one block, they took a different query. They also needed an additional query in order to basically recover the file, but that's not important for the security reasons. So the query looks very much different. However, instead of having EI naught here, I have C, where C is basically EI naught plus some vector beta with basically Hamming weight M. Yeah? It has only non-zero entries. Yeah? And by doing so, we can guarantee that C has at least M minus one non-zero entries, which means that basically instead of having only block back here, I have the delta dependent part spread basically among the entire matrix. And the hope was to avoid the subquery attack. And in its original form, the subquery attack doesn't work anymore. However, together with Svenja, who actually should give the talk today, we looked at this, and the first idea was Metzner-Kapdorowski also to look at this, but unfortunately it doesn't work up to D-1. So we would have had an attack basically up to T1 less, yeah, because basically since you have the error only outside of an information set, you could go up to n-k error weight. But it didn't work because they choose in the end n-k as the error. So we looked a bit into other approaches, and basically what we did, we adapted the subquery attack, so it works a bit differently. So we construct an auxiliary matrix, which then so we do not take out the blocks one by one, but we take like the first rows of each block, look at the auxiliary matrix, look again at the rank, and then by doing so, we can again look where the rank drops, we can recover the index. So it's a bit more sophisticated, but still the subquery attack works. And there were several follow-up proposals. So we were also in exchange with the authors. And in the end, unfortunately, there's no scheme at the moment that is secure, right? So, and that's it brings me back to the title of the talk. So security of code-based PIR, well, at the moment, it doesn't look good. There's some ideas about general statements, and so in general, there is other ideas. So there's, for example, a PIR scheme using codes over rings. Don't want to spoil too much, but there's also some concerns, let's say, and also a PIR scheme based on trapdoor hashing, but that's sort of a bit a different security assumption. So just to wrap up again, privacy in general is a separate goal. So the decoding hardness does not imply really the query privacy as we've seen, because it's not attacks on the McAleese setting. It's more an attack on this hiding this index. Then basically the main part here is the linearity, because all these rank computations, all the drops in the rank comes back to linear effects. Yeah, and basically what all the attacks have in common, they exploit this linearity in the end. And of course, error support restriction is risky. We know there's some schemes that use this. You just have to be careful. And a generic approach seems very difficult at the moment, but we're still working at it. Maybe alternative metrics could be interesting. Further directions also include nonlinearities, and also maybe don't use the standard PIR schemes as blueprints. Yeah, so I think what one did now is one took the McAleese scheme, one looked at the lattice-based scheme. If you look at lattice-based scheme, they look very similar. So maybe it's also the time to rethink the problem entirely and then come up with a code-based scheme. Okay, so that's it from my side. So thank you very much for your attention. And if you have questions, they're always welcome.
Thank you very much for the interesting presentation. Are there further questions? Yes.
Thank you for the interesting talk. Maybe I missed something. Since it's a post-quantum cryptography, what is the role of quantum computer in breaking it? So it seemed that only classical algorithms. The role of quantum is to apply Grover search to accelerate these classical tasks, or there are other quantum attacks?
Well, it's a very good question. So how is post-quantum crypto defined at the moment? So it's basically defined as classical cryptographic schemes that are resilient against the available quantum algorithms like Shor and Grover. Basically, it's usually only Shor and Grover. And if you take, for example, RSA or elliptic curve crypto, then you can break them using Shor's algorithm if sufficiently large quantum computers are available. Mm-hmm. However, for the underlying code-based problem, namely generic decoding, information set decoding, there's no efficient quantum algorithms. Grover, you always have to account for even symmetric, because you can always do the search. So that's why you say in Pre-quantum, if you want to keep the pre-quantum security level, you should double the key size, because that's exactly what Grover will limit your security level. But yeah, so for there's no such an exponential speed up algorithm to speed up this generic decoding problem.
And there are also quantum algorithms for linear systems, for solving linear systems.
Yes.
And are they taken into account here? So if the successful attacks exploit linear relations, then maybe quantum computer can even make situation worse.
Yes, this could be the case. Actually, in some other activities, we look into similar ideas, but more on the code-based primitives. Here, it's not even necessary, because that's polynomial time attacks. So you don't really care about further speedups. It's fast anyway. So,
okay.
Yeah, but it would of course help then.
So in principle, we can consider not just Grover, but also other like linear system solving quantum algorithms.
Exactly.
Okay, thank you.
Yeah. Welcome.
Are there further questions? If this is not the case, let's thank the speaker again. Thank you very much.